Good afternoon. We are going to start on lecture number 14 of electric drives course. So we had been discussing about braking in DC motors. So in that we specifically discussed about regenerative braking of a separately excited DC motor drive. So what we said was, if I have a separately excited DC motor drive, which is being supplied by VA on the armature side, and let's say the field is at a constant value, so the excitation is going to be constant. Under this condition, if it is motoring, I'm going to have a back EMF which is having positive and negative like this. And as far as VA is concerned, this is going to be positive and this is going to be negative. So I'm going to have an IA flowing into the armature. So I'm going to have TE equal to K phi times IA. And this is going to be a motoring torque or positive torque, which we call as motoring torque. So this is going to be under motoring operation. When we talk about motoring operation, this is the way it will be. And if we are looking at the magnitudes of VA and EB, we are going to have EB less than VA. That's why the current is flowing from VA to EB. So it is actually from VA to EB. So this is the motoring operation. Whereas if we are talking about regeneration, let's say EB becomes greater than VA. EB can become greater than VA only if at a constant excitation, only if the speed is increasing. Previously, the speed was probably something like omega m, whereas now the speed is going to be greater than omega m, much higher than omega m. So due to which I'm going to have plus here and minus here. Still, I have this as EB dash, let us say, and we are having VA here, which is a fixed value. And in that case, if EB becomes greater than VA, then IA reverses its direction. So once IA reverses its direction, because IA is reversing its direction, we are going to have the electromagnetic torque. If I try to look at what is TE, K phi IA, and IA is reversed in this particular case. So we are going to have braking torque or reverse torque. The speed is in the same direction, but the torque is reversed. That is the reason why we call this as braking. And please note that if I had a battery here, so the battery is actually getting the current into its positive terminal. So this is positive and this is negative. So the current is flowing into its positive terminal, which means you are going to have the battery getting charged. So it is regenerating. It is kind of taking in the power from the machine. The machine is working as a generator, which is converting the kinetic energy stored in its rotating parts into electrical energy. And that's how we are getting this particular battery is getting charged. Okay. So if I look at what is the kind of power this battery will be receiving, we are going to have EB dash as the voltage which is generated by this machine. So EB dash minus IARA, whatever is the drop across the armature resistance, that is going to be equal to VA according to Kirchhoff's law. So we are going to have VA multiplied by IA as the regenerated power or the power that is being delivered to the battery. So this is going to be the regenerated power. Okay. So VA times IA is the regenerated power. So the loss that is taking place within the armature still will be IA square RA. This will be the loss within the armature. So we said that this kind of regenerative braking with the fixed voltage can only allow reducing the speed to less than the no load speed. The moment it comes to the first quadrant of operation. So if let us say this is TE and this is going to be omega. So if we say that the nominal characteristics are something like this. So if originally the operating point had been somewhere here, and if due to increase in speed, slowly the operating point shifted towards this side and maybe it reached somewhere here, which is operating point B. Originally it was operating point A and now it is operating point B. In that case, you are going to see that the machine is developing a negative torque. So you can see that the torque is negative. So because of which you are going to have reduction in the speed. So slowly the machine is going to traverse this characteristics. And once it reaches in the first quadrant of operation, then again the torque will be positive. So it will not be able to regenerate anymore or supply back the kinetic energy after converting into electrical energy anymore. It cannot do that. So if I want regeneration on a continuous basis, so let us say if this is the torque axis and this is the speed axis, and let's say I'm going to have multiple characteristics like this. This is the first one, this is the second one, third one, fourth one, and so on. So I'm going to have this for different values of armature voltage. So let's say this is VA1, this is VA2, this is VA3, this is VA4, and so on for different values of armature voltages. So originally, let us say my machine was operating at this particular point. So when the machine was operating at this particular point, if I abruptly change the voltage from VA1 to VA2, then I will not be able to change the speed immediately. So what will happen is the operating point will shift to point B here. So because it has shifted to point B here and it is a negative torque, what I am getting here is a negative torque. This is going to come down in terms of its speed. So it will come into from second quadrant, it will come into first quadrant. And once it reaches, let us say point C, then again I can reduce the voltage further to VA3. So I can look at what is the kind of speed I'm going to achieve. So if I just drop directly what is the speed, if I try to drop a perpendicular to the speed axis here, so it is going to reach the point D now. Okay, so like this, you should be able to slowly reduce the voltage from VA3 to VA4 and further down, and then ultimately reach literally zero speed. So if I try to draw one more characteristics like this, so this is VA5, and that is definitely going to reach zero speed when I reduce the voltage to VA5. So with variable armature voltage, we should be able to incorporate regeneration even until zero speed is attained by a motor drive. So regenerative braking, the major advantage is going to be that you are converting the kinetic energy into electrical energy and feeding it back to the mains or the battery. And that is essentially saving or conserving a lot of energy. Whereas if I am applying a mechanical brake, as I told in the last class, the entire energy is going to be converted into heat because you are essentially using friction to stop the wheels from rotating any further. So regenerative braking results in a huge amount of energy saving. So this is the case with separately excited DC motor. But if I look at regenerative braking in series motor. Whether it can be accomplished in series motor. So I want to see whether it can be accomplished in series motor. So in the case of series motor, as we all know, we are going to have this as the armature and this as the field. Both of them are in series with each other. So this is going to be F1, F2, and this is going to be A1 and A2, which are armature terminals. And if I apply a voltage here, which is going to be V, so this is V in, input voltage. I'm writing this as V in because this is common to both armature as well as field. So this is going to be positive and this is going to be negative. So the current is going to flow in this particular direction. So current flows from F2 to F1 in the field, and A1 to A2 in the armature. Okay, so in which case, if I try to look at what is the torque is going to be K phi times IA. Okay, and I'm going to have the back EMF like this. A1 is going to be positive, A2 is going to be negative, and this is going to be the back EMF. So when I want to incorporate regenerative braking, I want basically EB to be greater than V in for achieving regenerative braking, right? So if I want to achieve regenerative braking, let us say I'm having the speed of the machine like this. So this is omega. So let us say speed is increased. Maybe this machine is fitted in an electric vehicle, which is moving down the gradient. So this is the road and it is moving down the gradient. And here is the car that is having the series motor. Okay, so it is moving in this particular direction. So in which case, if speed is increased, then we are going to have EB can become greater than V in. So if this becomes greater than V in, now let me just draw this once again. I'm going to have this as the armature and I'm going to have this as the field, and this is F1 and F2, and this is going to be A1 and A2, and I'm going to have EB greater than, EB is going to become greater than VA. So the current is supposed to flow now in this direction. If EB is greater than VA, I has to flow in this direction, whereas previously I was flowing in this particular direction. So now IA reverses. So also is IF. Both IF and IA, both reverse. So TE, which is equal to K phi times IA, this will not reverse because TE we also said is proportional to I square. So TE does not reverse. And T is not reversing, and you are going to have the torque and speed, both of them aiding each other. So I'm going to have the speed also in this direction, torque also in this direction. Both are going to be in the same aiding, they are going to aid each other. So this is not braking. This is not going to be braking. So if at all I want to incorporate regenerative braking, then what I need to do is to reverse at least the field. So if I want to reverse the field, what I need to do is, if this is my armature, and I'm going to connect the field in such a manner that this gets connected here and this gets connected here. So I am going to have F1 here and F2 here, and this is A1 and this is A2 and I'm going to have EB here with plus here and minus here. EB is greater than V, let us say. So in that case, I'm going to have actually the current flowing like this. It will flow like this, and the field current will still flow from F2 to F1 and back to the mains. So this is the way it is going to flow. So if I disconnect the field and reconnect the field in such a manner that still the current flows from F2 to F1, then TE will have K phi multiplied by IA. Now IA has only reversed, whereas phi has not reversed. So in which case this is going to be K phi multiplied by minus IA. So TE will reverse in this particular case if I am able to disconnect the field and reconnect it somewhat like this. So in a series motor drive, it is essential to disconnect the field and reconnect it like what I have shown here. Otherwise, it's not going to work properly for regenerative braking. But in general, regenerative braking being implemented in a series motor drive is a little bit more complex because of this disconnection and reconnection of the field. So much so for regenerative braking. Now, the next one that we are going to look at is dynamic braking. So we are going to look at dynamic braking, or this is also sometimes called as rheostatic braking. So in this particular case, what we are going to do is under normal motoring operation, I'm going to have the armature like this. And these are A1 and A2 terminals. And the armature current is flowing in this direction, and this is going to be plus and minus, and this is the armature voltage that is being applied in a separately excited DC motor. Now the field is here, this is F1 and this is F2, and the field current is flowing in this particular direction. So this is the normal motoring operation. In dynamic braking, what we are going to do is to disconnect this armature voltage, and instead we are going to connect a rheostat. So this is going to be my armature again, and I'm going to connect a resistance, which is a variable resistance preferably, and I call this as the braking resistance RB. I'm going to connect it right across this, and I'm going to have my field here. So this current, what is flowing here, that is going to be still IF. And I'm going to have the back EMF. Earlier, I had the back EMF again with plus here and minus here. Now also, I'm going to have the back EMF here with plus here and minus here. So the current is going to flow in this direction. So IA is reversed now. And if you look at the speed previously was like this. This is going to be omega m. And now again, this is going to be omega m. This is going to be the speed. So the speed is in the same direction, but the power supply is disconnected and the braking resistance is connected across this particular armature terminal. So this is A1 and this is A2. So if I look at the torque is going to be K phi multiplied by IA. IA is reversed. So I am going to have TE reversed. So which means this is braking. So this is dynamic braking operation for the separately excited DC motor drive. And if I look at what is the kind of current I'm going to see, so in this particular case, I'm going to have IA equal to EB divided by RB plus whatever is the inherent armature resistance. So you have to choose this RB value in such a manner that this current is not exceeding whatever is the limit that can be tolerated by the DC motors, commutator and brush assembly. So if I try to draw the characteristics corresponding to dynamic braking, normally I'm going to have the motoring characteristics like this. So if this is TE and this is going to be omega, this is the way the characteristics are. So probably the original operating point was somewhere here. So this is the original operating point for the DC motor. Now what I have done is to make VA equal to 0 during dynamic braking operation. So that means I have to draw a characteristic which will be parallel to this original characteristics, but starting from 0 voltage. But I have also included a large value of braking resistance. So if I include a large value of braking resistance, this should become steep. So let me extend this characteristics to the other side. So this is corresponding to only RA, whereas this is corresponding to RB plus RA. And here VA is a finite value, whereas here VA is 0. Okay, so from this particular operating point, if I just say that the speed remains the same, then I'm going to have the operating point shifting to point B. From A, it will shift to point B. And then now, because it is developing a negative torque, so you can see that this is the negative torque that it is developing. So the speed is going to come down because we are going to have J d omega by dt equal to TE minus TL. Now TE is also a negative value. So I'm going to have a very rapid reduction in the speed. So I would see that the speed comes down like this, along this. So as the speed comes close to 0 speed, the torque decreases tremendously. So if I want to really have a good amount of torque all the time, maybe I have to reduce the resistance. So let me draw this. So I have to, if I reduce the resistance, I should have another characteristics like this, another characteristics like this. As I decrease the resistance, it will become from the steepness of the characteristics essentially decreases further and further. Originally, it was quite steep. You can see that this was very steep. Now this has become less and less steep. So if this particular characteristics is traveling from point B, it is traveling like this. At this point, I'm going to reduce the resistance. Then again, the torque increases slightly. Then again, I can reduce the resistance. So this is essentially RB decreasing. So if I'm able to adjust RB value appropriately, I would be able to get a good amount of braking torque. So if I reduce sufficiently the resistance value, I'll be able to maintain a good amount of braking torque, what I have shown here. So in dynamic braking, unless I adjust the value of RB appropriately, I will not be able to get a good amount of IA, especially with EB decreasing. So I have to adjust along with the speed decrease, I have to adjust the braking resistance value appropriately. Another thing is, so this is the case with separately excited DC motor. If it is a shunt motor, I am going to have this as my EB. Originally, I should have had my EB originally like this. And I'm going to have on the armature side, I'm going to connect a braking resistance. So this is a variable resistance, which is RB. And I'm going to have the field connected here. Okay, so the field is actually being supplied by the generated EMF itself. So this is going to be IF and this is going to be IA. and both of them are going to be supplied by the armature. So I'm going to have this as IA. So IA is going to be equal to, rather, this is I braking, I should say. This is not IA. I should write this as I braking. So IA is going to be the sum of IB plus IF. Both of them are going to be added together to yield armature current. So under this situation, you are going to have actually as the speed decreases, because the torque is going to be negative, so speed is going to decrease. So if speed decreases, EB decreases. If EB decreases, then IF will also decrease. You are not going to have the field current as a constant, what was the case with separately excited DC motor, where IF was a constant. That is not going to be the case here. IF will also decrease. So EB will decrease further, because EB is going to be equal to K multiplied by phi, which is actually because of the IF value. Whatever is the field current, that is going to cause the flux. So the flux is also going to decrease, and you are going to have the speed also decreasing. So EB is going to decrease tremendously. So if I try to look at the shunt motor, how that undergoes regenerative braking. So this is TE, and this is going to be omega. And let us say originally the characteristics was something like this. So this is where originally my motor was operating. Okay. So if I include a braking resistance, which is corresponding to some particular value, so this is going to be RB plus RA put together. Now from this point, from A, it is going to move to point B. This is going to be the operating point now. So if it has moved here, slowly the speed will decrease, but beneath the particular speed, the back EMF becomes extremely small. The speed also becomes small, and IF will also become very small, that it will not be able to develop a good amount of braking torque at all. So you would see that initially it is following these characteristics, and abruptly now it is going to hit zero speed by means of friction. So there is not going to be any electrical braking happening here. Beyond a particular speed or below a particular speed, you are going to see that the dynamic braking does not take place. Instead, it is going to be only because of the friction that it is going to come down to zero speed. So dynamic braking is not as effective in the case of shunt motor as compared to a separately excited DC motor. So you would see that dynamic braking is more effective in a separately excited DC motor, because IF remains as a constant in a separately excited DC motor as compared to a shunt motor. So we are comparing a shunt motor with a separately excited DC. Okay. Now, if I try to look at the series motor for dynamic braking, quickly I'll make a mention of this. So this is going to be my series motor with this as F1 and F2, and this as A1 and A2. And during motoring, I'm going to have the current flowing in this particular direction. So this is going to be IF and this is going to be IA. So this is during motoring. When I want dynamic braking, I am going to again have my armature like this. And this is going to be the field, which is F1 and F2. Armature current will reverse if I'm going to connect a resistance at the terminals of the DC motor. So I'm going to connect a resistance here, and this is going to be a variable resistance RB. Now, when I connect the armature and field together, I should do it like what we spoke about regenerative braking. So I should just reverse the field and connect it like this. So if I connect it like this, I can see that now the back EMF is like this, and that is the one which is going to drive the current. So armature current flows in this direction, and it is going to flow like this, flow this way. Now it is going to flow from F1 to F2 still. So the field current is going to flow in this direction, and it is going to flow through the braking resistance. So I definitely need to disconnect and reconnect the field in such a manner that the field current retains the same direction, whereas the armature current is in the reverse direction. So the torque is reversed. The torque is going to be reversed so that braking operation takes place. So this is generally the way the dynamic braking is implemented in a series motor drive. Again, the field has to be reversed for implementing dynamic braking in the case of the series motor drive. So two things need to be done. Disconnect the power supply and connect the resistance, which is a variable resistance, and the field has to be reversed. So these are the two things that need to be done in the case of series motor drive. The third type of braking is plugging or reverse current braking. So we are looking at now the third type of braking, wherein we are going to reverse the power supply, and hence the current is also going to reverse itself. So let us say, first of all, during motoring operation, this is the armature, and here is the field. So I'm going to have field current flowing in this direction and armature current flowing in this direction. And I'm going to have VA, which is applied like this. Now I'm going to have the back EMF, which is in this particular polarity. Okay, so this is motoring. So during motoring, I'm going to have EB is equal to K phi omega, and we are going to have VA minus EB equal to IA RE. Now maybe omega is in a particular direction like this. Okay, so now TE is going to be equal to K phi IA. So this is going to be positive. So this is the motoring operation. Okay. Now for plugging operation, what we are going to do is the motor is already running. So it is running at a speed of omega, whatever we had already designated. And EB is also generated because of this particular omega as well as the field. So I'm going to have the field current flowing in this particular direction. Field current has not reversed. So I'm going to have the back EMF exactly, flowing in the same or generated in the same direction. Now, what I'm going to do is to connect the voltage source to the armature, but with the reverse polarity. Previously, this was plus and this was minus. That is why IA was flowing in this direction. Now I'm going to make this as plus and this as minus, and VA is going to be connected in this direction. So what is going to happen is a current will flow in this particular direction. So IA is reversed. What is more, VA and EB both are aiding each other. This is minus, this is plus, this is minus, and this is plus. So you are going to see that VA and EB aid each other. So we are going to have VA plus EB divided by RA is going to be IA. So unless I deliberately take some steps to reduce the amount of current that is being drawn. So for that, for reducing or for limiting IA, a large series resistance is needed in the armature. So we need to connect a large series resistance in the armature circuit. So what we are going to do is to connect a large series resistance like this. So this is going to be RP, plug-in resistance. So a large series resistance will be connected such that IA is limited and hence torque is also limited. So in this particular case, what we are doing is we are drawing power from VA and we are wasting that also across the resistance and also by generating a braking torque. And that apart from that, we are also wasting the kinetic energy stored in the rotating parts. So both the energy drawn from VA as well as the kinetic energy stored in the rotating parts, both are wasted during plugging. So to draw the characteristics corresponding to plugging, so let me first of all draw the normal motoring characteristics. So this is going to be TE and this is going to be omega axis. And we are going to have the normal characteristics somewhat like this. This is going to be the normal characteristics. So if I draw this for plus VA, so this speed is VA by K5. If you may recall, we wrote the expression for speed as VA divided by K5 minus TE divided by K5 whole square multiplied by RA. This is what we wrote as the expression for speed. So this VA by K5 is going to be the no load operating point. So this is the no load operating point. That is the speed at no load. Now, if I reverse the voltage, I have to draw the characteristics exactly in the other direction. So this is the third quadrant, which is corresponding to the reverse voltage characteristics. So this is going to be minus VA divided by K5. So if originally I had been operating the motor somewhere here, so this is the original operating point of the motor. If I have to see with minus IA where the operating point is going to be, it will go beyond the board. Somewhere beyond the board it will go in this direction. So instead of really making the torque as well as current so high, I should try to actually limit it by including a large resistance in series with the armature. So this is corresponding to RP plus RA, whereas this is only with RA. This is also only with RA. Now, when I have RP and RA put together, now the operating point shifts from A to B. Originally, the operating point was A. Now it has shifted to B. Now what will happen is the motor will try to travel. Now the motor characteristics will travel along this. So even at zero speed, if I don't disconnect the power supply, the motor will start running in the opposite direction. So the speed as well as torque both will be in the reverse direction. So this is the reverse motoring quadrant, which is third quadrant, whereas this is going to be forward motoring quadrant. So we can call this as the plugging characteristics, which is in the second quadrant. And the moment it reaches zero speed, we have to disconnect the switch. So very often we may have a speed sensitive switch, something like a centrifugal switch, which will actually sense where the zero speed is coming up. And at that point, VA will be disconnected so that the motor does not run in the reverse direction. Okay. So at omega equal to 0, VA will be disconnected. So this is essentially the plugging characteristics for a separately excited DC motor. Whereas if I look at the shunt motor, normally I should have seen that the field and armature are connected like this. So if I say this is F1 and this is F2 and this is A1 and this is A2 and this is VA with positive here and negative here. I'm going to have the current direction. This is going to be IA current direction and this is going to be IF current direction. But the moment I reverse VA, so I'm going to have now, this is the armature connection. So the field connection I'm going to still show as though this is F1 and this is F2. And here is my VA. Okay, so this is going to be VA. With positive here, sorry. So VA is going to be the other way around because during plugging we connect it in the opposite direction. So VA is going to have positive here and negative here. So very clearly I'm going to have IA flowing in the opposite sets. But if both IA and field current both reverse, in that case the torque is not going to be a braking torque. So that is the reason why I have to disconnect and reconnect the field in such a manner that the field current does not change its direction. So I'm going to have the field current still flowing in such a manner that it is going to flow from F1 to F2. So this is the way the field current is going to flow. So in a shunt machine, so this is the shunt machine motoring, whereas this is the shunt machine which is plugging. So the field has to be disconnected and reconnected in such a manner that the field current does not reverse its direction. That's extremely important. So if you look at the series machine, again in a series machine also, we need to disconnect and reconnect the field. So this is the motoring operation of a series motor. So I'm going to have this as A1. This is A2 and this is F1 and this is going to be F2 and this is VA, positive and negative. So I'm going to have the current flowing in this direction from A1 to A2 and F1 to F2. So this is going to be I. Okay, so this is going to be the motoring operation. For plugging, I am going to have still the direction of field should not change. So let me draw the motor once again. So this is the motor and this is going to be the field. Okay. Now, if I say that here is the terminal from which the power supply is going. So this is F1 and this is F2 and this is going to be the power supply. So I'm going to have plus here and minus here, and this is going to be whatever is my VA. So I want basically the current, armature current to flow now from A2 to A1, whereas the field current should still flow from F1 to F2. So from here, I would connect this to F1, and from here, I would connect this to A2. So the current would flow still in this direction, and from F1 to F2, and the current would flow this way from A2 to A1 and back to the negative terminal. So field connection should be reversed during plugging in both series motor as well as shunt motor. Okay. So if I look at the three methods of breaking the DC machines, regenerative is the most energy efficient method, whereas plugging is going to be the least energy efficient method. But very clearly, if I am looking at which can give me the quickest response, obviously plugging will be able to give me the quickest response because I am generating the reverse torque with the help of a power supply also. So I'm trying to actually connect a power supply in the reverse direction. So I will be able to get the quickest response with plugging. So if I want to stop abruptly, then plugging will be the best method if I want a very quick response. But if I am worried about energy efficiency, in that case, regenerative braking will be the most energy efficient method. Now let us try to do a couple of problems in braking. So let me try to first start with a problem, a numerical example for regenerative braking. So the problem statement is somewhat like this. It is a 220 volts shunt motor. Okay. And it has an RA of 0.0620. EB is equal to 215 volts at 960 RPM and at rated excitation. Okay. And under this condition, we should be able to definitely calculate what is the torque. I don't think that will be a big deal. Now, what is being asked is at what minimum value of speed, at what minimum value of speed, a load torque of 172 Newton meter, 172 Newton meter can be held by means of regenerative braking. So this is the question. So a 220 volts DC shunt motor has RA equal to 0.062 ohms. It develops a back EMF of 215 volts at 960 RPM and at rated excitation. At what minimum value of speed? A load torque of and at a load torque of 172 Newton meter can be held by means of regenerative braking. So let us try to solve this problem. The first and foremost thing is, it says at 960 RPM, it develops 215 volts of back EMF. So we should be able to calculate what is the back EMF constant. So back EMF constant at rated excitation is going to be equal to 215 divided by omega. So that is going to be 215 divided by 2 pi multiplied by 960 divided by 60. Okay, so this comes out to be 2.14. So this units will be volt second per radian. So 2.14 volt second per radian is going to be the back EMF constant K5. Okay. So I should be able to calculate at 172 Newton meter. If I have to develop a torque of 172 Newton meter to hold a load at certain height or something like that, at 172 Newton meter, what is the armature current value? If I try to calculate that, then what I need to do is, I know that K5 IA is the torque. The torque is generally given by K5 IA. So I should say, what is IA from here? IA is going to be 172 divided by K5, which is 2.14. So this is K5, 2.14. So I should write this as 172 divided by 2.14. And that will give me the current value, which happens to be 80.374 ampere. So I'm assuming that the excitation is constant throughout, that is not changing at all. Now, in regenerative braking, if you may recall, I am going to have EV greater than VA. So this is VA. And this is going to be plus and this is going to be minus. And I'm going to have EB also like this. And I'm going to have IA flowing in this particular direction. So I'm going to have EB minus IARA, that is going to be equal to VA. And VA is given here as 220 volts. 220 volts is the armature voltage. And resistance, armature resistance is given as 0.062. So I should be able to calculate EB equal to VA plus IARA, which is going to be VA is 220 volts and IA is 80.374 and RA is 0.062 ohms. So the total voltage comes out to be 225 volts. This comes out to be 225 volts. So I can calculate what is the speed corresponding to 225 volts at rated excitation. At rated excitation, K5 will be a constant. So K5 will not change. That is not going to change. So I should be able to write this as 225 divided by K5, which is 225 divided by 2.14, which is actually giving me 105 radians per second. So this corresponds to 1004 RPM of speed. So at what speed it is going to hold this particular torque means with the given value of K5, it is going to hold the load at 1004 RPM and it is going to generate a negative torque such that it is able to hold it at a speed of 1004 RPM and 172 Newton meter is the load torque. Okay. So this is a problem corresponding to regenerative braking in a shunt mode. This is a shunt mode. Okay. Please note that in shunt motor, even if I have the field here, the field current direction is going to remain the same whether it is motoring or it is regenerative braking. Field current will be only in one particular direction. That is not going to change. You don't have to reverse the field coils at all in regenerative braking in the case of a shunt machine. So let me try to do one problem in reverse current braking or plugging. So the problem statement goes as follows. So it is 220 volts, 20 kilowatt shunt motor has a rated speed of 1200 RPM. Its efficiency is 88% and RA value, the armature resistance value is 0.10. This motor is braked by plugging. So the first question is, if the braking current has to be limited to 2 times I rated, then R braking equal to what? What should be the braking resistance that should be included in the armature circuit? That is the first thing that is being asked. Calculate the corresponding braking torque. That is the second subdivision of the question. The third one is calculate the torque when the speed reduces to 400 RPM. Of course, we have to assume that plugging is implemented by reversing the field connection, because we already said that plugging in a shunt motor requires the field connection to be reversed so that the torque generated is a braking torque. So let us try to solve this problem. So first and foremost thing you have to realize is 20 kilowatt, whatever is given, that is actually the output of the motor. Any of the electrical machines, what is given as the power rating, that is the output power rating that we normally talk about. So 20 kilowatt is the mechanical power output. So 20,000 divided by the efficiency is going to be input power. So this is 20,000 divided by 0.88. So that happens to be 22.727 kilowatt. This is the input power. So let me call this as P input. And the input power should be the product of VA and IA, or whatever is the input voltage and input current. So I should say this is equal to VA IA. And if you look at the shunt motor, if you want to be really accurate, you're going to have the armature like this and field like this. And the total current drawn from the power supply is going to be the summation of, if I say this is IL, and let us say this is going to be VA. What I have connected here is VA with plus here and minus here. I'm going to have IL as the summation of whatever is IA and this IF. So IA plus IF is going to be IL. But generally, I'm going to see that IF is much, much less than IA. So IF can be neglected. That is the reason why I'm writing the input power as VA multiplied by IA. Otherwise, I should say P input is VA multiplied by IL. That is what I should be writing, but this is approximately equal to VA multiplied by IA. So I can calculate IA rated, that is going to be equal to 22,727 divided by 220 volts. That is going to be the IA rated value. So IA rated comes out to be 103.3 ampere. This is IA rated value. Now, I should be able to write the current has to be limited to something like 103.3 ampere multiplied by 2, because twice rated current when the plugging is being implemented. So when plugging is being implemented, the current has to be limited to twice the rated value. So during plugging, I'm going to have VA plus EB as the total voltage. And the total voltage divided by the total resistance, that should not exceed this twice the rated value. That's what they're saying. So the first and foremost thing I need to do is to calculate EB at 1200 RPM and rated IA when the machine is drawing rated IA. So I'm going to write this as EB equal to VA minus IARA. VA is 220 volts and IA is 103.3, and the resistance, armature resistance value is given to be 0.1. So 220 minus 10.33. So that actually will give me whatever is the back EMF, that happens to be 209.67 volts. Now I should say VA plus EB divided by RA plus R external should be less than or equal to 2 times 103.3 ampere. So in this particular case, we know VA, we know EB, we know RA. We also know the armature current limit. So from which we can calculate what is R external. So R external comes out to be 1.98 ohm. So the external resistance that needs to be connected, that happens to be 1.98 ohms. Now, what is the braking torque? So braking torque during plugging at 2 times IA rated. So if I know for sure that what is the kind of torque I am getting at rated current, I have to just double that. That's all. So this is TE rated multiplied by 2. That is going to be the plugging torque. So that can be calculated as, so rated torque is 20 kilowatt divided by whatever is the speed in radians per second. That is 2 pi multiplied by 1200 divided by 60. So this is going to be the rated torque, and this has to be multiplied by 2. That will give you exactly whatever is the torque corresponding to twice the rated IA, and when you are just starting plugging with the back EMF being 209.67 volts. The next subdivision, what is being asked is, what is the braking torque at 400 RPM? So the first and foremost thing we need to do is to calculate back EMF at 400 RPM. This will be 1/3 of EB at 1200 RPM. So EB at 1200 RPM already we calculated as 209.67 volts. So I should be able to calculate this as 209.67 volts divided by 3. Okay. Now we need to calculate what is the current. So IA at this speed, that will be VA plus EB dash divided by 1.98 ohms plus RA, because 1.98 ohm is the external resistance we have included. So both of them put together, when I just connect it, then I'm going to get a current corresponding to this. The current happens to be 139.37 ampere. So I should be able to calculate what is the power or what is the torque. The torque I can calculate either as K phi IA. We can calculate K phi as whatever was the original value of voltage I got for 1200 RPM. So that is 209.67 divided by 2 pi multiplied by 1200 by 60. This will be the back EMF constant in volts second per radian. So this is the back EMF constant. So once I have the back EMF constant, I should be able to calculate what is K phi multiplied by IA. IA is 139.37. So this torque comes out to be, in this particular case, 232.55 Newton meter. And if I want power, I have to multiply this 232.55 by the speed, which is 2 pi multiplied by 400 by 60. So this is T multiplied by omega. So this is exactly the power in watts. Okay, is this clear? So this is the problem corresponding to reverse current braking. We look at one more problem corresponding to dynamic braking in the next class.